The other thing I wanted to do is actually talk a little more general about why I think emergence in general is a good way to think about physics. And this has a bit of a more of a philosophical way of thinking. And it actually connects directly, as I will make clear, to the main theme of information. So here's a brief outline. I'm going to talk about emergence and information. This, as I said, is more of a philosophical perspective I have on how we think about science. We should think about science. Then I will go more into the details of emergent gravity. At least I review a little bit what is going on, the essential ideas and some recent developments. And then eventually we want to get to more connection with observations, maybe in terms of looking first at the sitter space. And at the end, I want to talk about a model that I already presented actually last year in the online, or 2 years ago in the online version, which is some ideas related to this Hubble tension. We had some talks about this before, and so I'll present this here because I also want to have some feedback from the experts here in this room. So let me just start generally. I mean, emergence, I think many people know already what is emergence. I mean, it's just the idea that instead of having reductionist point of view, where everything can be derived from everything microscopic, like you go from atoms to molecules to life and things like this, you have this other idea that there might be things happening at larger scales or in complex systems, which cannot be simply derived from the underlying microscopic theory. And it's not like everything is determined from the small. Also, there may be things happening at larger scales that somehow connect back to the short distance scales. And I think one of the reasons why we think about emergence is also the fact that we as human beings are making up our theories from our brain and so on. And there's some way in which we should also realize there is a limitation to what we can do. This is indeed the slide I wanted to have, namely, in physics, we're very good at developing theories. Actually, we have very successful theories of the very small. And if you think about the 20th century, I think it was a reductionist way of thinking that brought us very far. Namely, we want to understand the world, and many people thought that we have finally understood all the things about elementary particles and also the theory of general relativity, which is so successful. I think this is a reductionist way of thinking, but there's the other view that we should then maybe have, which puts itself also in the middle of this, because all of this have been derived from our way in which we deduce information, or we get theories out of absorbing information. Like in the universe, we generally are very good at understanding what is happening at very large scales and also at very small scales. Physicists tend to avoid most of the things that are happening at human scales, and maybe because that's even more complex. And I think there's a reason for that. If you look at our theories, usually the theories of the very small are very beautiful and simple. And actually also the models that we make of our cosmos are generally quite simple, but described with very few parameters, while the actual world around us is much more complex. And so what I think we're doing when we're looking at nature is really, I actually took this picture from the cover of Roger Penrose's book, is really make a model of the world. We have the physical world, which we're observing. Then in our brain, we eventually develop a model, which is then sort of our Platonic world, where these equations that we derive are living. And this is where I also think the link with information comes from, because in our process of observing the physical world, we are actually reducing the model into some abstraction. I mean, the physical world is complex. It has many things going on, but our models of nature are abstract, and they amount to a reduction of information. And as I'll make clear, actually information so what I mean by information, by the way, is not just what we call information, which is useful to us. It's also the information you would need to really describe what's all going on in this whole complex world around us. Because what we're doing in our brain is actually forgetting a lot of information. And this is sort of why notions like entropy actually come into the game, because entropy is a way of keeping track of how much information we have forgotten. So I think information and emergence are very much related. And this is also my point of view of how nature works, that eventually we're reducing, well, what we're observing at least is a reduced form of the information that is actually there. And so this is how I define emergence, is that we indeed observe phenomena which at a macroscopic scale are derived from something at a microscopic scale where it has no a priori meaning. For instance, in this picture, there are pixels, But when we look at larger scales, we see mountains, trees, and so on. And a certain way you should think about this as emergence concepts. So my view of the world is like this. We live in a world full of information, and we somehow, our brains must sort of make this into our physical laws. And this is also what happens in gravity. So in gravity, we have discovered that entropy plays a very important role. And you may wonder why that is the case. So what is entropy? It's a notion that is introduced in thermodynamics to basically describe what is the amount of information required to describe the microscopic state, say, of all the molecules of a gas. And you can basically think about entropy as indeed the number of bits that is required to describe this. And then there are derived emergent notions like temperature and so on that are basically derived from statistical mechanics. They describe the average energy per microscopic particles. And actually entropy plays an important role because it actually can lead to forces. So this is something that I taught to my students when I was teaching statistical physics, is that there are forces in nature that are purely thermodynamic in origin. And one of the famous examples is that of a polymer, where you have a polymer that curls up. In itself, the polymer has no ability to create a force, but when you put it in a heat bath, simply because it wants to occupy the most entropic state, it wants to shorten. And then if you have a bead attached to it, which you pull, you actually can measure a elastic force. And that force is known to be entropic in the sense that its magnitude is determined by the temperature. If there's no temperature, actually this elasticity would go away. Sometimes it's misunderstood that entropic forces have to do with changes in entropy, which is not actually the case. I mean, the force is actually needed in order to make sure that things happen adiabatically. And we know indeed that an elastic force is reversible. Actually, it's described by a potential. That indeed means that there is no actual change of entropy, but just the fact that there is an entropy playing an underlying role actually can be used to derive this force. And the reason I'm telling you this is that because I want to apply the same principle to gravity. And of course, in gravity, we know that we also have a conservative force where if you describe it in Newtonian way, you would have a potential and so on. So this idea was sort of in my mind when I was thinking about why does gravity have something to do with information or with entropy. Of course, that came from all the work that Bekenstein, Hawking, and actually Penrose played an important role in this as well, in deriving what we now call the laws of black hole thermodynamics. That is namely the observation that the horizon area plays the role of an entropy in the way that if we would write down the gravitational equations of how black holes behave when, for instance, you merge or you throw other things into the black hole, the horizon always increases, and you can even prove this, which was the area theorem by Hawking. But then the actual formulation became that of a set of laws that looks exactly like the laws of thermodynamics, which we know we can derive from statistical physics. So this is one thing, but then also the question is, why is gravity so special that somehow it knows about this microscopic, well, about this entropy or something like that? And this is where indeed, well, this idea of emergent gravity, first of all, comes around. So what is emergent gravity? So the fact that we can derive statistical physics from, so I should say, thermodynamics from statistical physics is actually the fact that we can derive in particular the first law, which tells you that when you change the energy, there's also associated change in entropy, and the proportionality constant is given by the temperature. This you can also apply to black holes. And in that case, the entropy, as I already told you, is the area of a horizon. And the temperature has to do with the acceleration, the gravitational acceleration at the location of the horizon. And then you can write down the same law where the change in energy becomes the change in the mass, and the change in entropy then translates to the change in area. And this law actually is equivalent in some form to the gravitational laws. Now, the idea of emergent gravity is that there should be a microscopic explanation of these equations, simple, in the same way that we know that we can describe the microscopic origin of thermodynamics. The other thing that I focused on in a paper I wrote a long time ago, which was sort of on this entropic gravity idea. By the way, I think the name entropic gravity is perhaps even better still than emergent gravity, because emergence is a very general notion. Entropic makes clear that what it emerges from is really the entropy of some microscopic system. And by now we actually know that this entropy should be thought of as sort of an entanglement entropy in the structure of quantum structure of space-time. The other thing we have to understand is not just the gravitational laws, which are like Newton's law or the Einstein equations. I mean, those are laws that we generally associate with gravity, but there's another force aspect of gravity, which is just inertia. The fact that the mass determines the force by if we want to accelerate is something that we need to be explaining as well, because when we are really thinking about explaining what gravity comes from, or what even the space-time geometry comes from, then the first thing you want to know is why do objects move in the way they do, and why does it require a force when we start accelerating an object. And so this is a thought experiment that you can do. And one thing that I learned is that you can actually apply the same reasoning as I did for this polymer idea, namely that there is actually an origin of this inertial force, which has to do with the fact that there's a temperature. I mean, I told you that a force, well, first of all, in Newton's law, a force requires an acceleration. I mean, that's what Newton's laws tell you. But also what we learned is that there's a temperature required to get a force if it's an entropic force. And indeed, the temperature is proportional to this acceleration. So one thing that you find is that you can naturally explain why the force is proportional to the acceleration if you start from this microscopic point of view that I first explained the temperature, and then you can derive the origin of the force. Actually, in the talk that follows by Manes Visser, he will continue in this theme about what is really a microscopic way or well, a way of thinking about this origin of inertia. It's questions that also Lenny Susskind has been thinking about. I mean, there are many papers have been appearing actually since the original paper that I have written about 10 years ago. For instance, well, Lenny has a paper which is called Why Do Things Fall? And indeed thinking about sort of more this question, I mean, his idea is also that the actual origin of the force has to do, or why the things fall, has to do with a microscopic process that requires this information that is contained in the space-time. So this is indeed the recent developments that have been going on are all centered around the interpretation of this Bekenstein-Hawking formula, not just for black holes. Also, these horizons appear when you accelerate, and they appear in any part of space-time that even look like the vacuum. And the current interpretation is that this formula actually explains the describes the entanglement entropy between two sides of space-time when I have a horizon. The horizon can be thought of as sort of a surface that is created. Then if you accelerate one direction, you create a horizon somewhere in space, and then you basically split the space into two parts. And entanglement is then a property that tells you that the quantum states on one side sort of are connected to the quantum states on the other side. And this is even what sort of leads to the ideas of connectivity. And the formula that described it, and is something that has been verified very explicitly in certain models, is that indeed the entanglement entropy is equal to the area of a certain surface that we put into space. And this is called now also the Ryuta-Keniagi formula that has been derived, as I said, even in some microscopic models. And indeed, in these same models, people have derived the Einstein's equations using this first law. And actually, this whole program of emergent gravity basically has been completed in a setting where the space-time, well, unfortunately, has no cosmological constant. It actually has a negative curvature. It's called ADS space. And in that space, people have exactly done what I said before, namely derived the Einstein's equations from this first law of basically entanglement entropy. So there's a way that the entanglement entropy is the origin of this force.